Hi, I wanted to clear up some confusion that I might have caused about exponential equations. So I was trying to simplify some things when probably I shouldn't have. Um, and I made a mistake in a problem that I did in class, and I'd like to clear those things up. So I said that one way you can look at growth, exponential growth, is you can say the amount that's present at time t equals your initial amount, it should be the naught, times your growth factor, let's call it b, raised to the t. Now that is true if the growth factor you have is for your given time unit, so like per year or per week or something like that. So for example, a population triples every hour. Let's make it be a population of bacteria. If you currently have 1,000 bacteria, and it has been 3 hours. How many did you start with? Okay, so we currently have 1,000. That's the amount we have right now. We don't know how many we started with. It triples every hour, and it has been 3 hours. So we have 1,000 equals A naught times 27, or A naught equals 1,000 divided by 27, or A naught equals 37. So I started with 37 bacteria. Okay, but that's because they tripled every hour. What if it was a unit of hours, or a multiple number of hours? So what if I said instead that the population triples every 2 hours? Well, there's two ways I could go about doing this. I could figure out, well, how many time periods did I have? So I could use the same formula where I would have A of t equals A naught b to the t, and I would say, okay, well, within my 3 hours, how many 2-hour periods did I have? How many 2-hour periods did I have in those 3 hours? And to do that, it was supposed to be a t, I would take my 3 and divide it by 2. So the 3 hours is the amount of time I actually had, and the 2 hours is the tripling time, and I get 1.5. So that tells me I had 1.5 tripling periods. And so I would work the problem with 1,000 equals A naught, 3 to the 1.5, and that is 1,000 equals A naught times 5.196 and then divide both sides by 5.196. And I get 192. So in this instance, I started with 192 bacteria, and what I did was I took my actual time and I divided it by the time, my doubling time or my tripling time. Okay, the other way that you could do it is, rather than dividing before you plug in, you work it into your formula, and so this would give you a slightly different looking formula. It would look like this. The amount at time t equals your initial amount times your growth rate times t over n, where n equals the growth period. So in this case, if we had our same bacteria problem, so the same problem as before, we would write it out as 1,000 equals A naught times 3 to the t, and it was 3 hours, over our growth period was 2. And then you can see that ends up with exactly the same problem that we had up above, with A naught ending up being 192 bacteria. Okay, so let's apply this to some other problems. Actually, before we do that, let me show you one other way to do it. And this is a way that works when you have no idea what the growth rate is, and you have to find the growth rate. And we're going to do this in the next section, so this is just kind of a preview. So let's say that a population of bacteria has 20,000 cells now. 7 hours ago, it had 500 cells. Write a formula for the amount of cells at t hours. Okay, so we could say, well, we went from 500 to 20,000, that is times 40, and so we could say it goes up by 40 times every 7 hours, but that's not usually how we do that. And usually the way we do this is with the formula that has E in it. So the amount at time t equals your initial amount times e to the kt, and this k is telling us our rate, and that's what we would solve for. So we know that we have currently 20,000, and we started with 500, and we need to find k. We don't know k, but it has been 7 hours. So to solve this, we divide both sides by 500. And we get 40 equals e to the 7k. And then to solve this, and we'll see this in the next section, you take the natural log of both sides. So the natural log of 40 equals the natural log of e to the 7k. The natural log of 40 equals the natural log of e to the something is that something. The natural log and the exponential function are inverse functions. They cancel each other out. So that's 7k. Divide both sides by 7. The natural log of 40 divided by 7 is 0.527 equals k. And so my formula is the amount at time t equals a naught e to the 0.527 t. Okay, so, or in this problem, whatever we started with, I think it was 500, so 500 e to the 0.527 t. Okay, so that is a very general form. Okay, now going on to look at some specific problems. The half-life of zinc 71 is 2.4 minutes. If one had 100 grams at the beginning, how many grams would be left over at after 7.2 minutes has elapsed? So we could write this, we could do this in two different ways. So we could say the amount is the initial amount times the half-life raised to the t over 2.4, because it halves every 2.4 minutes. And so in this instance it says after 7.2 minutes, so we can say 100 times 1/2 to the 7.2 over 2.4, which is 3. So this is A equals 100 times 1/2 to the 3rd. And that gives me 12.5 grams. The other way to do it is to say that I've got my starting amount times my growth rate to the time, and I just need to figure out how many time periods I have. My half-life is 2.4, and I've had 7.2 minutes. So 7.2 divided by 2.4 is 3. So I have 3 half-lives. So our amount is 100 times 1/2 to the 3rd, which is 12.5 grams. Okay, similarly, after 24 days, 2 milligrams of an original 128 milligram sample remain. What is the half-life of the sample? So we have 2 milligrams remain of 128 times 1/2 to the t. This will get us the number of time periods it took to get down to 2 from 128. So 2 divided by 128 is 1 over 64 equals 1/2 to the t. So what power would you raise 1/2 to get 64? Or 2 raised to what power is 64? Well, 2 to the 3rd is 8, and 8 times 8 is 64, so t is 6. So t is 6, so there have been 6 half-lives. And it has been 24 days. And so that means that the half-life, if there have been 24 days and 6 half-lives, then the half-life has to be 4 days. Okay, now let's look at a problem that was like your homework problem number 7. A population of amazing reproducing gummy bears was introduced into a region, I guess a very sugary region, 15 weeks ago. Gumologists suspect that the population doubles every 5 weeks, and the population is now 960. Assuming none were eaten, what was the initial population? Okay, so we have the amount at time t equals the initial amount times the growth rate to the t, but we want to divide it by the growth period, and the growth period was every 5 weeks, so t over 5. So the amount we have now is 960, and that equals our initial amount times, it's doubling every 5 weeks, so that's our growth rate to the t over 5. But it's been 15 weeks, so our t is 15. And so this is 960 equals a naught times 2 to the 3, or 960 equals a naught times 8, or a naught equals 960 over 8, which is 120. So we started with 120 bears. Now, the other way to think about this is it's been 15 weeks. The doubling period is 5 weeks. So we have had 15 divided by 5 equals 3 doubling periods. So we have doubled 3 times. So you can say that our 960 was divided by 2. Well, if we divide 960 by 2 3 times, we can get back to where we started. So we divide it by 2, and then divide it by 2, and then divide it by 2, and that should get us back to where we started. 960 divided by 2, and then divided by 2, and then divided by 2 gets me 120. So our initial amount was 120. So what is a formula? A general formula would be A equals 120 times 2 to the t over 5. And then that's part B. And then part C, estimate the gummy population 8 weeks from now. Okay, so we are currently 15 weeks from the starting period. So 8 weeks from now, will be 23 weeks. Never trust my addition. So to find the amount we would have 8 weeks from now, we would take 120 times 2 to the 23 over 5. And I get, and we have 2,910 rounded to the nearest bear. 2,910 gummy bears. Can you guess what kind of snack I'm having? Okay, so that's how many you would have.